On all this way.
Thanks very much, Alan. Good afternoon, everybody. So I've got about 360 slides, so I hope you all have the afternoon ready to watch this for a bit. You good? All right. So there really are a lot of things to talk about with regard to automation of stations or building projects using microcontrollers. There's many ways to take it. What I want to do is give you kind of an overview in two ways. A little bit about the technology and a little bit about what you can do with that technology. And let me give you a little bit of background on myself as a start. So I've been a ham for a bit, as many probably here have. I really focus on two things. I built a lot of repeater systems. I'm on the board of several repeater networks and all that. But I also like to do HF. I built a lot of QRP kits. I've built a lot of the Sierra radio kits. I built all the Elecraft kits. And then about 7 years ago, John Best, KJ6K, and I, we're both members of the same repeater club. We decided that we wanted to build a repeater controller, and that's what really started us down the path of building projects with microcontrollers. So we've spent the last 7 or 8 years working on various projects, and we want to share with you what we've learned in that process. So here's a little bit of a shameless plug. We started 7 years ago, and we built a repeater control system that's being used by lots of big networked systems around the country. And about 1.5 years ago, we came out with a new product which we call a ham stack. And what we found was a lot of our friends that were repeater guys that were interested in what we did building the repeater controllers wanted to get some advice about what chips and languages and what approach you would use to building your own project. And we didn't really have a very good answer. There's a lot of things out there on the market, but we didn't really feel like there's anything really tailored to the ham radio user. So we built the platform that we wish we had before we started building our repeater controller. And then we started building some example projects that we thought were so interesting, we've actually made them into kits and in some cases assembled things that you can get to automate your station. So I've got two sections to my presentation. The first section to the, thank you, you noticed. The first section of the presentation is an introduction to what is a microcontroller, some of the tools that you could use with that kind of technology. And then the second part of the presentation walks through several examples. Now, tomorrow in the forum, I'm going to do a very similar presentation. The difference is, this presentation I'm going to talk more about the technology, and in tomorrow's presentation I'll talk a lot more about the projects, but I'll briefly touch on them to give you an example of how you can use these parts. Before we go any further, let me just take a quick show of hands. How many of you have designed or built anything with a microcontroller in the past? Simple or complicated? Okay, and everybody else is here either because you're interested or you're just tired, right? So I won't ask. I couldn't take it. So for those of you who have built stuff with microcontrollers, hopefully there'll be something new. Feel free to ask questions at the end, and then we'll kind of go from there. So why are microcontrollers relevant to the ham, and why is this time a very interesting time to start working with them? I think there's 4 reasons why things are really coming together right now. The first reason is there's a lot of very powerful chips on the market. When I was starting to do digital design many years ago, we would have a CPU chip and a memory chip and an EEPROM and a UART and a PIA and a bunch of junk, and you'd make a circuit board this big, and I can buy a single part that's that big that does all of that and more for a couple of dollars. So the chips are very powerful. The second thing that is really essential is it has to be easy enough to program. And most microcontrollers, up until the last few years, you usually program them in assembly. It was very low level. You had to be intimately familiar with the guts of the part. Or you would use something like a basic stamp, which is a higher level language, but the hardware wasn't particularly powerful. No offense to the basic stamp folks, but it's just not something you're going to build a real commercial product out of. So today there's a lot of high level language compilers that are very good, and they're very productive development environments. The third thing is we're seeing the emergence now of what I would call a standardized hardware platform. In other words, there's circuit board geometries and pin configurations that multiple vendors are building to that makes the components interoperable, that lets you take a board from this guy and a board from that guy and plug them together and take a compiler from somebody else and build your project. So that's very helpful. And lastly, there's a huge and growing community of people that do this. And I'm here to tell you, most of them are not hams. Most of the people that are really into this are the typical electronic hobbyist kind of guys who may well be hams too, but you see a huge uptick in the interest in this at places like the maker fairs, where everything is going automated in one way or another, and they're using these kind of technologies. So those are the 4 reasons why I think this is really a hot topic. Now, what would you do with a microcontroller? There's everybody's got a pet project or two that they can imagine. All of these kind of projects could be built with a microcontroller. But what is a microcontroller? So what do we mean by that when we say it's a microcontroller? So my definition of a microcontroller is pretty simple. It is typically a single part, a chip, that could look like this, and it's got a bunch of stuff. It's got everything you need to do most of what a project takes to get done. It's got a processor core that does the actual code execution. It's got memory to store the program. It's got memory to store temporary variable storage, maybe some flash memory for data, and a bunch of I/O. This is one of the most interesting things about these microcontrollers. They have a lot of special purpose peripherals built into the part already. Not only digital I/O, A to D converters, serial ports, high-speed serial buses, pulse width modulators, timers, all that stuff is built into the chip. So for a couple of bucks, you get a pretty powerful little package to start with. Now, you can buy a microcontroller from any one of these companies. Some of these guys sell to particular industries, some sell to very general kind of market. The ones that the hobbyists tend to use the most today are either Atmel or Microchip. So I would say probably Microchip has the longest history really in this space. Atmel a little bit newer for a lot of good reasons. I think over the next few years you'll see a lot more work on more sophisticated SoC or system on chip chips, which are ARM-based, which also give you the ability to move into a Linux platform to do more complex embedded control. But for the most part, we're going to focus on these kind of traditional embedded controllers. Now, in our case, we chose to use Microchip about 7 or 8 years ago, which turns out to have been a very good decision for us. Everything I'm going to say you can pretty much apply to Atmel and many of these other vendors. So I'm going to illustrate what I know with the parts that I know, but what I'm going to tell you is pretty much true for many of these other parts and products as well. Now, when you go buy a microcontroller, the first thing that you want to do is figure out which platform you're going to use. And when you buy it, it sort of comes in different form factors. You can go buy the chip by itself, or you can buy a little bit of a hybrid module like a basic stamp, which is essentially a chip at the end of the day. Or you can buy a circuit board that's got that microcontroller built into it and a few little peripherals like a voltage regulator and some connectors. Most of us start out by buying a chip and building up from there. What we've seen in the last few years is with the growth in the use of the Arduino platform, which is based on Atmel, a lot of people just start with that as the base and they build out from there, which is a good way to go. The platform that we built is identical to the Arduino, but it uses a microcontroller. And we could spend 3 days debating the pros and cons of Atmel versus Microchip, and it's really not a very interesting conversation. So if you'd like to do that, we'll do that some other time. But we use the same kind of pinout and the similar kind of part, but our platform is a little bit, in our opinion, a little bit better. But so, you know, what's a PIC? A PIC microcontroller is a part by a company called Microchip Technology. Several years ago, they shipped their like 6 billionth part. Every rice cooker in China has one of these chips in it. I mean, these are ubiquitous. They are in every cheap automated thing you can imagine. So they're all over the place, and they're very common in ham radio products. But don't be fooled. So if any of you are old enough to remember, when I first learned to program, I learned to program on a VAX 11780. So some of you might be that old to remember. The VAX 11780 was about the size of 2 big side-by-side refrigerators. It was a 32-bit mini computer. That thing ran about 1 million instructions per second. The Microchip PIC that we use in a lot of our projects runs at 64 megahertz, which translates into 16 million instructions per second. That's pretty good. So to give you some gross idea, you know, that's a pretty powerful little part just in terms of its throughput. There's a lot of stuff that's on that chip, and I'm not going to go through all this in the time we've got, but there's a processor core, there's memories, there's I/O, there's a lot going on in that part. And if you look at the specs, man, there's a lot of specs. These things have brownout timers, they have watchdog timers, they've got all kinds of stuff, and they come in various configurations. When you pick a part, you're sort of buying into the family. When you buy into that family, there's a range of different microcontroller parts you can choose from. Some of them have more pins. For example, the 26K22 is a 28-pin package. That exact same chip is available in a 40-pin and an 80-pin package. It's the exact same core, it just has more I/O registers. So depending on what you're building, you can have more and more direct I/O. Now you'll notice once you get above 40 pins, you'll also go from a dip package into a surface mount, in this case what's called a quad flat pack, which means you have to surface solder very fine wires, which is sort of difficult for most of us. So most of our projects we use a chip of this size, the largest number of pins on a through-hole dip package, which gives you about 30 I/O pins. It's really a pretty flexible part. So hooking one up, if you're doing your first simple project, what do you need to actually make that part work? You don't need that big circuit board with a ton of parts, you need very few components. So I need my processor chip, I need a crystal. The crystal down here is the basic time base for the part. In the case of the microchip parts, you can take that crystal frequency, multiply it by 4, so that 10 megahertz crystal will actually make that chip clock at 40 megahertz, which is pretty fast. You need a bypass cap on the power supply, you need a jack to plug in the in-circuit programmer to download the code, a couple of pull-up resistors, and you're good to go. That's all you really need. So in this little example, the only thing this part will do is I hooked up one of the I/O pins to an LED, my status LED. When you learn to program, what's the first program that you write? What is the equivalent of Hello World in hardware?
Flash, flash, flash.
Blink the LED. And even if you're building a fancy project, the LED is really your friend, because you're always, you want to check and see if something's working, and that's a kind of good way to do it. So you can just drive the LED directly from the microcontroller. And you still have a bunch of I/O pins. Now, those I/O pins, in the good old days when you bought a part, every pin had a purpose. If you had a UART, a serial port transmit pin, that's what that thing does. In these parts, every one of those pins can be software programmed to serve as 2 or 3 different functions. Not simultaneously, but you can select what you want those pins to do. So for example, I can have some of these pins be analog to digital converters where I'm reading a voltage. I could have other pins be a digital input or a digital output. I could have other pins be a high-speed serial interface or a pulse width modulator to control a motor, or one of many other kinds of internal components. So there's lots of those things built into the chip. So here's a simple circuit. I'm going to add a digital input. So all I need is a wire with a pull-up resistor, and I can pull this low or let it float high to get a digital input. My digital output, maybe I want to drive a relay, so I could put a transistor or a little buffer chip to now close the relay. And maybe I want to read a voltage, so I might have a series resistor to limit the current going into that part. Maybe I add a voltage divider because I want to scale. To me, measuring 5 volts in the ham station is not very useful, but I want to measure 13.8 on my power supply or my batteries, so I'll just put a voltage divider, and now I can measure 30 volts or 20 volts or whatever. That's all I need. So with this circuit, I could measure my battery voltage and then open or close that relay, and the code to do that is like 6 lines of code. Not much to it. So why not use that? A lot of projects are built with things like 555 timers. I've got a lot of buddies who build, satellite stations or contest stations, and they're building a TR sequencer, and they got 6 555s and R's and C's, and and I say, well, how do you reprogram it? And they say, well, you get out the soldering iron and you change the part. So with something like this, you can make a TR sequencer with like 20 lines of code. It's really simple. If we add a serial port, we need a chip that'll convert the TTL level 5-volt logic to RS-232. It's a simple part with a few capacitors. Now you've got a serial port. Not much more complicated than that. Now, if you want to build this project of yours, there's many options out there. One option is you can download a piece of software from one of several vendors. The software is free. You get a schematic editor, you get a board layout program, you design your circuit board, you give them your credit card number, and they'll gladly send you as many circuit boards as you want. Now, the thing that's really cool about this is, in my mind, I think it saves you a lot of time and headache, because when I would do a project, I'd get out a piece of vector board and a bunch of sockets and a bunch of wire and spend 2 Saturdays, point-to-point wiring my project and mess it up. What I found is I could do a board layout and get the thing right the first time, and it looks really professional. And I could do that board for as cheap as 20 bucks a board. So, why would I ever do point-to-point wiring? I'd much rather do this. And this is what those tools look like. This is a picture of one of the boards we did. This is a 2-layer board. It's got one of those 80-pin surface mount processors on it. All the other parts are through-hole components, and you can see the top and bottom layers simultaneously on the layout. You can also put the silkscreen annotation for the part values or the reference designators right there on the board. Now, another option is to go with a pre-existing prototype board. There are a million companies which will sell these things to you. They typically have some basic set of component lands, like a place for the microcontroller, a voltage regulator, a USB jack, and a bunch of proto board space. There's more expensive ones that already have a bunch of handy parts pre-instantiated on the board. Some people I know use these boards as their project. That's a little more expensive, but it's another way to go. The other thing you can do is start with a basic platform like an Arduino or a Hamstack or a basic stamp and kind of build up from there. Now, on the software side, software is really simple. Wouldn't you all agree? I mean, the hardware, that's hard. But software, whew, that's really easy. So actually, software is not that bad. You write your software, you compile it, you download it, and you run it. What could be easier than that?
Yeah, right.
Thank you. There's a reality check from somewhere out there, and I'm sure. Now, what's really interesting about the microcontrollers, years ago, you had 2 choices. You either write in assembly, which is great if you do it for a living, or you would write in BASIC running on an interpreter like a BASIC stamp, which is fine for a 10-line program, but totally inappropriate for a complex project. Forget doing interrupts, forget doing any real-time applications. You really want to write code that's going to execute really fast, give you a lot of high-performance features, but you don't want to be a professional coder to have to do it. Now, you could start with a assembler if you want to. You can download the microchip assembler for free from their website, write an assembly code, and that would be great. I personally don't ever do this. We wrote assembly code for our repeater controller for the very lowest level code, but we would never do that normally. There's no reason to. Because you can write in C, which is a much higher level language, and a much more reasonable way to approach the problem. And similar to the assembler, the microchip C compiler is free. When we started working on our repeater controller, we bought the professional version of that compiler. It was 500 bucks. That exact same compiler you can download today for free. The only difference is that we have an extra optimizer in the compiler, which makes the code a little bit smaller. But unless you're doing a really nutty big project, you don't need that. So the $500 compiler is essentially free, and it's a very robust compiler. There's also lots of libraries. So you can write your code in ANSI C. You can call library functions to do string manipulations, motor control, whatever you want. Now, an alternative to that, which I personally kind of prefer, is writing in BASIC, but it's not the old interpretive BASIC, it's a real compiled BASIC. So there are 3 or 4 companies that make BASIC compilers for the microchip parts, and this is not your father's BASIC. I mean, if you learn BASIC, when I learned BASIC, you would never use that BASIC because it had line numbers and it was stupid. This is a modern structured programming language with full flow control like any other structured programming language. You've got arrays, you've got variables, you can declare variable types, you've got if, then, while, do, for loops, you can do string manipulations, you can do data type conversions. There's tons of libraries for motor control, for serial port control, for shift registers, all kinds of pre-existing libraries, just like for the C compiler. So if you're a C guy or you're a BASIC guy, you can use the same hardware platform and write in one of those languages or go back and forth. Now, once you've written your program, you then use a different program in a little programmer. This little programmer plugs into your USB jack, and it takes that compiled code that the compiler generated and it squirts it into the PIC processor. And that just downloads that code into the chip. In the old days, we would have an EEPROM, and you'd have to program the EEPROM, you'd erase it, then you'd program the EEPROM, and then your thing wouldn't work, then you'd erase it, and you'd reprogram it. Well, you don't take anything out of the socket. You plug in the programmer, you leave it there, you compile, you download, you run, oh, it didn't work. Change your code, compile, download, run. So it's very quick turnaround. It takes less than a minute to download the program into your chip, usually about 30 seconds. So here's our little LED flasher example. And then here's the basic structure of the program. Every control program has a basic structure like this. You start and initialize the variables in the environment. You read a bunch of inputs. You decide what to do about it. You write a bunch of outputs, and you do this until you die. That's all they do. It's a gigantic control loop. So here's our little LED blinker. This is an example written in BASIC. I tell the compiler which chip I'm using, how fast the clock is going to go, that I have an output pin, and then here's my little loop. While true is always true. Now you can have an equation while pin number 3 is at ground, then loop until it's not. It's easy to do. In this case, I'm just looping forever. So while true, bring this pin low, in other words, put it to ground, delay 200 milliseconds, bring that pin back high, delay 200 milliseconds, and loop forever. LED will blink forever. That's your hello world right there. You can do the same thing in C. It takes about just as much code. Syntax is different. So you can do the same thing with the same amount of effort with the C compiler. Yes, sir. Yes. So the gentleman's question is, do we use Swordfish? There are at least 4 commercial basic compilers that I've used. And of them, I would say there's really 2. The 3 of them are really very good. The one that we use exclusively is called Swordfish Basic. It's very similar to Proton Basic. It's very similar to PIC Basic Pro. It's like Microelectronica's Basic, which is very buggy. But the other 3 are very good. So the Basic that we use, you can get a free version, or you can get the paid-for version. The paid-for version is $150. The free version is free. To the PIC Basic Pro. So PIC Basic has 3 different models of Basic. So the full version of the Swordfish Basic is equal to the full version, top version of PIC Basic Pro, but that's $250, and this is $150, so it's cheaper. Yeah, you can do full interrupt handling with the Swordfish Basic. I've programmed in the PIC Basic Pro compiler, but never with an interrupt handler. I've done it in the Swordfish, and it's not that bad. We can show you examples of interrupt in BASIC. All of our serial routines are all interrupt driven, so it's really no big deal. And we provide libraries to do that, so you don't have to do it yourself. It's off the shelf. Okay, now in the last few minutes, let me run through some projects to kind of give you some idea of things that you can do. All of these things are projects that we've done either as a one-off or things that we thought were interesting enough that we turned them into a little product. So this is our processor board. It uses a 18F46K22. The reason we picked that out of the other 300 parts at Microchip is that it is the fastest chip with the largest amount of memory with the most number of pins in a through-hole 40-pin package, which means you could build it. As you can see, it's got a lot of good specs. And we've also made a ton of accessory boards you can use with that platform. If you go to our website, we have a gallery of projects that people have built. And some are very simple and some are very fancy. We've got a DTMF controller and a keyer and an antenna controller and a GPS clock synchronization thing and a fan temperature controller. And they're really interesting projects to take a look at and get some ideas. So let me quickly walk through some of these projects. The first project that I'll share with you is at a contest station of Bruce W1GQ. He has a few more antennas than I do. And they're a little bit taller than mine are, but he's like more studly, so I'm not climbing a tower. Now his problem, not a problem I've got. he has a bunch of stacked Yagis and these expensive vacuum relays, and he needs to be able to switch the relays to change the phasing on his antennas. And so this is the solution that he built several years ago. So he's got, we didn't make it look bad, it really looks this way. So he's got this box on the tower to switch the phasing of the Yagis, and he runs a big umbilical cord back to the shack 200 feet away. It's got like a zillion wires and a mess of toggle switches. And he asked, like, well, what would you do? And I said, I wouldn't know how to do that. That's a lot of work. So this is what he did. He took this board, which has got 8 relays and some communications interfaces and some other stuff, and the CPU board, and then he built a control panel, and he replaced this mess with this. So the control head has got a bunch of buttons and an LCD display. You push a button, it sends a command over a serial port to the remote box that has this board. The serial port decodes the command and then actuates the relay. So the only cable is power going to the relay board and 2 wires for the data. So that's a little bit easier than this big umbilical cord. So he mounts that in a box, mounted in another box, mounted halfway up the tower, and then he presses the button, and he even customized the LCD to tell him what antenna configuration he's looking at. So this is a very straightforward project. This is the kind of project that really anybody who spends an evening really understanding the kind of tools, you could attempt a project like this, especially with all the libraries that are available. A lot of the building blocks are already there. Now, essentially what Bruce did was he went from a bunch of switches with a bunch of wires to a bunch of relays to a serial control over a Cat5 cable to a bunch of relays. The next phase of what he's going to do for the other towers is he's going to replace that cable with an RF data link. So since he did this, we've come out with these data radio modules, which essentially replace the serial cable with RF. And so any data that goes into one RF module pops out the other one. It's like having a wireless serial cable. And it is literally that easy. They just work out of the box. So this way you can have this thing like a half a mile away and remotely control it, no sweat. Okay, CW keyboard. This was a fun project. So when we did Field Day last year, so are any of you Elecraft customers? Okay, so we live in Silicon Valley near where the Elecraft guys are. So Wayne and Eric usually do Field Day with us. So Wayne brings the KX3 to Field Day, which is pretty cool. So the only known KX3 in existence is at our Field Day. So we're putting our fingers all over it and playing around with it. And so one of the guys says, "That's really cool, but I want to do PSK with the KX3, but I don't want to send CW or use a computer. Can you use a Hamstack CPU board to do the PSK?" And I thought, no, we don't do PS. Then I realized that the K3 or the KX3, you can send ASCII text into the serial port. And then we said, aha, we could do that. So what we did was we built this. We took the CPU board and a breadboard, and what we put on here was a cable that goes to a 6-pin connector for a PC keyboard, and then a DB9, well, you don't see it here. There's a cable that comes off of this with a DB9 that goes to the serial port of the K3 or KX3. And then we wrote a program that when you type on the keyboard, it generates the right ASCII string to send it to the K3 in the right sequence, in the right command structure. Then we said, well, what if you don't have a K3? What if you got, like, my T4XB? Well, I need to switch that like with a relay. So we put a relay on the board so you can also do straight key. So you press a key on the keyboard, and either it'll send straight key or it'll send the ASCII text to a Elecraft radio. And so we thought, well, this is really cool. And then the guys at CQ Magazine said, wow, that'd make a great article. So the June issue of CQ, this next issue, will have an article in it about doing having a KX3 in the field for Field Day, and it'll show our prototype of this little project. So since then, we made a circuit board that basically took everything on the proto board and made it into a nice circuit board. And so that's going to be in the issue. What we also did was we used some of the function keys on the keyboard as macros. So you can do F1 is CQ, 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 F2 is 599, of course, whatever. And we published the source code for that as open source, so you can download it from the website. And it's even if you don't care about this project, it's a really good example of a relatively simple program that you can write in BASIC that uses that PIC platform. And by the way, no one ever wrote a program from scratch. If they don't, no illusions to that. You will take someone else's code, you will steal it, you will then start hacking it. So we give you a lot of stuff to hack away on. So the next project we did was an audio mixer. The short story on the audio mixer was, in my house, my operating desk is next to my teenage son's computer desk. And if you have a teenage son, he's probably wearing his headphones and playing a game where he's killing somebody. And this is me, and this is my son. Okay, get the illusion. So I thought, well, something's got to give because I can't hear the radio. So I thought, I'll get a pair of headphones. Problem solved. The problem with the headphones is I can only listen to one radio. And a lot of us have, what can I say? So how do you solve that problem? And so what I came up with was a box that took speaker audio in, did a bunch of stuff, and the output went to one speaker and one set of headphones. So what we built was a audio mixer, which will take audio from 4 radios. It'll take the audio in, it'll process the audio, it'll let you switch the audio, it'll mix the audio, it will let you amplify the audio to an unamplified speaker and go to a set of headphones with a low-pass filter to take all the hiss out of the headphones, because when you put in your earbuds that are good at 20 kilohertz, you don't want any components over about 5 kilohertz. So we want to take that out. So we built an audio switching board to do that, and that's what it looks like. So this is everything I just described, and you might notice up here there's a row of pins. And what could that be for? The row of pins is for the processor. So what we did was we took our CPU board and we mounted it to the top of that audio mixer, and then we said, well, that's great, but we want to do transmitter switching also. So we came up with another board that does switching between 2 or 4 transmitters to one set of user devices. So I have my Heil headset, and I've got my Vibraplex key or key paddle and all that jazz, and I don't want to be changing all that mess to go from radio to radio. So with this switch box, I can select one of 4 receivers or all 4 simultaneously, and one of 2 or 4 transmitters, and switch all that stuff around. So the transmitter switching board sits on the top. You can actually go even bigger. You can go up to 8 receivers and 4 transmitters, and that's what the board looks like. There's the PIC. And now one of the things that's a question that we get often is how RF immune is a PIC, how RF sensitive is a PIC. And we've put PICs in very high-powered transmitter sites, commercial broadcasts, two-way cellular sites for the last 8 years. And we've never had RF interference, and we've never had a part fail or behave badly because of RF. We've also never had really a hardware failure. One of the things that we found is that these are kind of 5-volt old-fashioned parts. If you stick with the 5-volt parts, they're pretty rock solid. So that's really kind of a little safety tip. So anyway, that's the switcher, and there's a breakout board, and there's the thing, and you can control it with switches or a program. It's really all controlled with a serial port. This is another thing you can do with a PIC. We made a hardware control head. It's got a PIC in it, and it's basically a dumb terminal. And so you can control that radio router gizmo either with the hardware or with a program. So one of our guys wrote a Visual Basic program that basically you press a button and it squirts a serial command to the router, and it performs the task and also gives you status. We also added OTRSP, which is gibberish for works with the logging program, contesting program like N1MM or WinTest. That's WinTest. So you can use that to do your SO2R switching if you're into that sort of thing. Anyway, that's all that. Another little project we did was we wanted to do some remote control at our repeater sites and some of the automated station stuff. So we took the CPU board, a bunch of relays, and we put a Wi-Fi module on top of that. And so the Wi-Fi module does a connection to the router or ad hoc to your iPhone. And so one of our friends writes iPhone apps. And so he's got a thing called Hamlog, which is a cool little logging program for your pad or your iPhone. And so we've added a remote control panel to the Hamlog, and you can send it control commands over the internet to switch relays or monitor the voltages or monitor the digital inputs off of that board. And we use that at a repeater site, so we monitor the battery voltage and whether the AC is active and the temperature in the room. And this is what the app looks like. So you see analog inputs 1, 2, 3, 4, digital input 1, 2, 3, 4. You can label it. And then this is a scroll. And you flip it, and it scrolls up all 8 relays. When you press a button, it squirts a command to the PIC. The PIC, if it decodes the command, it sends another packet back to the iPhone that causes the LED to change state. So you know that the thing actually happened. So we're just sort of trying to give you an idea of the kinds of things you could do with these microcontrollers. This was last 2 examples. This was one that someone sent us an email and said, well, what about doing a compass? And so we thought, well, that's a great idea. So we did a little research, and we found this Honeywell 2-axis magnetometer. And this little guy will send out your compass heading, your magnetic compass heading. So we got that working, and it talks over a serial interface called I2C. I2C is a 2-wire interface between the PIC and a peripheral chip. And you can see this is the prototype we did. There's the magnetometer, and it's a little test program we wrote on the PIC that tells you what the heading is with that thing. So then one of our guys said, oh, this is great. I want to put this on my tower. So we made him a board. We got a box. We mounted it in the box. And then you can strap that box to the boom of your antenna. So he's got on his 40-meter 2-element Yagi. And wherever the Yagi is pointing, we telemeter the data back to a little base station on 2 gigahertz. And then the guy that wrote the Visual Basic app, he extended that and added this pointer. So as the compass is, whatever the compass is pointing at, it's constantly streaming the magnetic heading. And this guy receives it, and the program interprets it, and then puts the pointer in the direction that the antenna is pointing. And then he built in a little offset. Doesn't show here, but there's a declination offset, so you get the actual correct pointing direction. And as you spin the magnetometer, you can see the needle loop around the page. I don't need one of these, but I thought it was pretty cool. So it's fun to see. The last thing that I'll share with you is a keyer project that we did. Every keyer that anybody has ever built probably was built with a PIC. So it's not like no one's ever done one before. But we had to do one too. So we built a keyer. The keyer uses the PWM, the pulse width modulator, plus an op-amp with a little filter to generate a very nice sine wave. So we can generate side tone coming off the PIC. So the PIC is a great tone generator, by the way. We have libraries to generate tones. It's very easy to do. There's an LCD to display the speed. So John, the guy that did this project, one of the things that bugged him was his keyer has a pot, but you don't know how fast the keyer is set for. It's just faster when you turn it to the right, slower when you go to the left. So he said, if nothing else, it's going to have the words per minute on the display. So as you change the speed of the keyer, it updates the display to tell you how fast it's going. By the way, this is not a pot. This is not a mechanical pot. It's a rotary encoder. So every time you move it, it increments or decrements a counter, which in turn speeds up or slows down the keyer. And then we added stuff like opto-isolated outputs. There's a high-voltage solid-state switch for doing grid block keyed old transmitters and stuff like that. And this was also a bit of a demonstration vehicle for we talked about having a lot of powerful tools to use. One of the things that we wrote that's really very powerful, if you're a C programmer, is our C library. Our C library has a lot of functionality off the shelf. So that if you incorporate our library into your program, you just write your application code, and it uses our library if the functions are required. And our library includes a bunch of timers, tone generation. You can generate multiple simultaneous sine waves, square waves, etc. We do CW generation. You do one subroutine call with a string, and it sends the CW for whatever that string was. We can do DTMF generation, real-time serial port handling. So one of the biggest problems you find is when you go from simple microcontrollers to advanced microcontroller projects. The difference is a simple project does one thing. An advanced project does 5 things at the same time, unbeknownst to you. One of the things that you wanted to do is to have the serial port constantly run in the background, constantly taking data and never losing a byte from the serial port while you're generating a sine wave while you're modulating the PWM for a motor control, while the display is updating the speed of the motor, and it better look like it's all in real time and happening at the same point. The only way to do that is to do an interrupt-driven application, which is not trivial. So we've taken some of that headache out of it by providing a library. We wrote the interrupt handler ourselves, so you just incorporate that in your code, and you just have to write your application code. So all these things will happen simultaneously. Plus, we added some other functionality that's not interrupt-driven, like EEPROM read-write and other stuff. And we're adding stuff constantly to that library. And that library is a free download. You can download it and use it and knock yourself out. So anyway, that's a little bit on the kind of projects you can do. I would suggest if you want more info, you're welcome to talk to me. We got a booth at the other side of this hall. We're doing several different sessions. Tomorrow there's a session here on building an automated contest station with microcontrollers. There's another session on doing development with C tomorrow. And I'll be doing another version of this presentation with more detail on the projects in the forums tomorrow. And if any of you are from the Northwest and are coming to Pacificon, we're going to do a whole track on embedded control projects there. So I kind of went over my time, but I'll hang around for questions. If there's a couple of questions for everybody, I'll be happy to take them now. Otherwise, I'll stick around for a few minutes. Yes, sir.
My question is
yeah. So, are you using the microchip C compiler? Yeah. So do you have a question or just a general observation? Yeah. Yeah, so there is. So his comment is, if I may, I've used the C compiler, and it's really complicated and difficult to use. And so my take on that is two things. One is, if you are pretty familiar with using development environments, it's pretty typical. But for most of us that do this for fun, and we want to do this for a couple of hours in the evening, it ain't fun. So there's a couple of suggestions. One suggestion is don't use C. Use the basic compiler, because the basic compiler is simpler and the syntax is easier to read, and you can build it up one line at a time, and you can go from a very trivial to a fairly sophisticated application in BASIC. So I would suggest looking at that. The other thing is, if you get into doing a complex program, you really need a lot of libraries, and you should look at using our library, because that will save you. The trivial things are simple to do, but the hard things are hard, and that's why we wrote the library, to help make some of those things easier to do. So you really sort of have a choice of whether you want to stick with C or go with BASIC. The IDE. Yeah, the Microchip IDE is a professional development suite. So there are a zillion choices and options and configuration things, and it does take it probably takes a good several evenings to kind of get really comfortable with that. The BASIC, you can get comfortable with that IDE in 5 minutes. It's an editor. There's a compile button. It shows you when it bombs what the problem was. It's much easier to use. So on the spectrum of easy to sophisticated, I think the C IDE and the C compilers are really best for medium to complex. BASIC is best for simple to medium plus projects. Not that you can't do the extremes, but that's sort of my personal take. Yes, sir. Yeah, thank you for that straight line, and 10% off for you. We have a booth exactly across the hall, against the wall over there. So please come by. I'm sorry. Yes, sir.
Is it BASIC more extensive code than C is?
Is either one more extensive or extensible? No, they're about the same, because the compilers have a set of intrinsic functions built in. Yeah. Both compilers, you can add library modules, and many people have written library modules. So, for example, last week I was at Fry's Electronics, and they had servo motors on sale, and I know nothing about a servo motor, but I always wanted to play with one. So I bought the servo motor, and I got home and I thought, okay, what do I do with this? And I don't even know how it works. And so I went on the web and I found some guy wrote a servo motor library module for Swordfish Basic, and I downloaded the module and I compiled the program, and now the servo's running. And you can come see it over here. I bought 2 more servos. It was, yeah. So there's a lot of add-ons you can do to extend the functionality.
For others here, okay, they haven't played with processors ever. Where do you start?
If you've never played with a processor at all, you know nothing about it, which is at least half the people that we talk to, by the way. But you just like to try, and frankly, you don't even know what you're going to use it for, but you want to learn. We recommend starting with, we have a pack to do that. We have everything in a box for one price, and it's a starter kit. And it comes with a manual, and it walks you through step by step, and it's a whole tutorial. It's a 100-page manual tutorial. It includes the basic compiler. It includes this pointer to the C compiler, but all the examples in the first version are in BASIC. So if you really don't have a religious bias towards a language and you really don't care, you just want to start, you want to pick it up and leave it off and come back in 2 weeks and pick it up again, I would use the basic compiler. Because it is, from the first line of code you write, it's pretty straightforward and the IDE is very simple. Now, all the projects that I showed you, 3/4 of those projects were all written in BASIC. And 1/4 of them were written in C. So you can do some pretty sophisticated stuff in the basic compiler. Now, we have a lot of people who also will come to me and say, you're out of your minds, real men code in C, and I would only code in C, even the LED blinking program, and well, okay. That's fine. I mean, there's nothing wrong with that. The amount of code's the same. It's just, like what you're comfortable with. So I think one of the problems in the past has been, if you go down the basic path, you are constrained to a particular vendor's stuff, and it's dumbed down. So the guys that do the basic stamp, those are totally underpowered, and they're not very good at doing multitasking projects. They're not very good real-time chips. They're severely memory limited. They're really, unless you go to a propeller, it's really not. And by the way, if I want 10 of them, they're a little pricey. If I want to build my own board and put a pick on there, that pick is like $5. So as opposed to $39 or $49.95 for just the chip from the basic stamp parallax guys. So I think that's a totally useless platform. And what if you want to try C tomorrow? Well, you're stuck. You're only using basic, and it's interpretive. It's not compiled, so it's not very fast. So in my mind, why use? It's fine to learn, but you run out of suds as soon as you're doing a serious project. Yes, sir. 2:15, I believe. We have the schedule at our booth on a little card you can have. Any more questions before we wrap up? Yes, sir. Linux. Oh, great question. That's a great question. So the short answer is, this class of processor really isn't appropriate to host a Linux OS. It's hypothetically possible, but you wouldn't get many services on it. So the interesting thing is there's a whole brewing community around Linux-based embedded controllers. There's one called the Raspberry Pi that was just announced, $35. It's a little Broadcom SoC on a board. Very interesting. You can't get them yet, but eventually they'll be out. Very cheap, very interesting. There's another board called a Beagle Board, which was built on a TI OMAP platform. It's an ARM processor also. Both of those run Linux. So I think that's a very interesting path to look at. But they're really different in the sense that if you really want to do an application where you really understand every line of code and it's very close to the metal, it's a hardware-oriented real-time control application, the microcontrollers are probably better for that. If what you want to do is have a lot of high-level services, like I want FTP and TCP/IP and all that stuff running on the processor, you need a Linux platform, or you need to offload the PIC with something else. That's really where Linux is valuable. So in our thinking, they're complementary. In fact, probably, depending on the application, a really interesting thing is to combine them together, where you have a host processor that's a Linux processor that maybe has an Apache server or is doing your network communications, but it's not going to be running real time. And then you have an I/O processor like one of these, PICs, that's doing the real-time data acquisition and control, and then you have a communication channel between the two. That's a really interesting combo for a system. So also, if you're freaked out by C, you're going to be really freaked out by Linux plus C. So that's a whole other reason why they're kind of different. So I think they're very complementary in the long run. Any more questions before we wrap up? Okay, thank you very much for your time.